Today we are going to continue to talk about verifying trig identities. By the end of this video, you should be able to recognize the difference between an equation and an identity, and you should be able to begin to verify trig identities. First, just a point of clarification. This is an expression. Expressions do not have equal signs. Expressions are what we worked on simplifying last class. This is an equation. This is only true for certain values of x. But this is an identity. This is true for all values of theta. So today, as we are verifying trig identities, we are going to show that using identities we already know, that one side of an identity is equal to the other side of the identity. For this, we will only work to simplify one side. And usually you want to pick the more complicated side. So, first we have secant squared of theta minus 1 over secant squared of negative theta equals sine squared of theta. So, we are only going to work on the left side. We're going to use identities that we have already learned and try to show that this is equal to sine squared theta. As when we were simplifying expressions, there is not one right path. Some methods will be a little shorter than others, but do what you see and go from there. So first, I'm going to start by using my even and odd identities to get rid of this negative theta. Okay. So I have used an identity that I already know so that this is the same as the fraction that we had above. So now I'm going to show you two different methods of where to go from here. One, I'm going to call the Pythagorean, because we're going to use Pythagorean identities. The other we'll call the fraction path. So, if you look here, one of our Pythagorean identities says that secant squared of theta is equal to tangent squared of theta plus 1. So let's go ahead and do that substitution. So we can simplify the positive and negative 1, they cancel out. So I have tangent squared of theta over secant squared of theta. Now I'm going to change these into sines and cosines. So I have sine squared theta over cosine squared theta. And then secant squared theta is 1 over cosine squared theta. So then, since I'm dividing fractions, I want to take this fraction, flip it, to give me sine squared theta over cosine squared theta times cosine squared theta over 1. The cosine squared thetas cancel out, and I just have sine squared of theta, which is what I wanted this to equal. The nice thing about verifying trig identities is you know what your goal is. You know when to stop simplifying, because it tells you what it's supposed to equal. Let's look at a different method. If I start here with secant squared theta minus 1 over secant squared theta, I'm going to split up this fraction. Then I'm going to simplify each of these smaller fractions. So I get 1 minus 1 over secant squared theta is cosine squared theta. And then I know from my Pythagorean identities that this is equal to sine squared theta. And I'm done. Let's look at another example. Here we have 1 over 1 minus sine of beta plus 1 over 1 plus cosine of pi over 2 minus beta equals 2 secant squared of beta. So I'm going to start by using my cofunction identities to simplify this. Then, since I have two fractions, I'm going to go ahead and get a common denominator. So I'm going to multiply this first fraction by 1 plus sine of beta over 1 plus sine of beta. Multiply the second fraction by 1 minus sine of beta over 1 minus sine beta. So then I have 1 plus sine of beta. I'm going to go ahead and combine these, plus 1 minus sine beta over, and if you multiply 1 plus sine of beta times 1 minus sine of beta, you get 1 minus sine squared beta. Now, sine of beta and negative sine of beta will cancel, so I have 2 in the numerator. And I know from my Pythagorean identities that 1 minus sine squared of beta is cosine squared beta. Well, I know that this is the same as 2 times 1 over cosine squared beta. 1 over cosine squared beta is just secant squared beta. And then I have times 2. And that is what I wanted it to be equal to. So we're good. Here I have tangent squared of x plus 1 times cosine squared of x minus 1 equals negative tangent squared of x. Again, I'm going to show you two different methods for this one. The first one I'm going to call the FOIL method. So we're going to go ahead and double distribute and multiply these two out. So I have tangent squared of x times cosine squared of x minus tangent squared of x plus cosine squared of x minus 1. Now I'm going to change to sines and cosines so I can simplify this. So I have sine squared of x over cosine squared of x times cosine squared of x minus tangent squared of x plus cosine squared of x minus 1. So my cosine squared of x's cancel out, and I have sine squared of x minus tangent squared of x plus cosine squared of x minus 1. Well, I have sine squared x plus cosine squared of x, which from the Pythagorean identities I know is equal to 1. So I have negative tangent squared of x plus 1 minus 1, which is just negative tangent squared of x. So we're done. Another method uses the Pythagorean identities. I know that tangent squared of x plus 1 is the same as secant squared of x. I also know if I rearrange my identities that cosine squared of x minus 1 is equal to negative sine squared of x. Well, secant squared of x is 1 over cosine squared of x. So that gives me negative sine squared of x over cosine squared of x, which is negative tangent squared of x. Either method will get you to the same result. Let's look at one last problem. I have tangent of x minus cotangent of negative x. So first I'm going to use my even and odd identities to get rid of this negative x. So I have tangent of x plus cotangent of x. I'm going to switch to sines and cosines. Then I need to get a common denominator. So I'm going to multiply by sine of x over sine of x and cosine of x over cosine of x. So I end up with sine squared of x plus cosine squared of x over sine of x cosine x. The numerator is one of our Pythagorean identities, so I have 1 over sine of x cosine of x. Now, we can split up this fraction so that I have 1 over sine of x times 1 over cosine of x, which gives me cosecant of x times secant of x. We want secant of x times cosecant of x, so we just switch the order because multiplication is commutative, and we are finished. So these are just a few examples of some things that you might see as you are verifying trig identities. As we discussed in the last video, switching everything to be in terms of sine and cosine can be helpful. Sometimes you need to split up fractions, sometimes you need to get common denominators.